All right, welcome. Let's get started. Last time in class I gave you a handout to help you with this problem where the water can flow through one of three different pipes. That handout was actually originally developed as kind of like an in-class example that we didn't end up having time to solve last class period. And so the steps that are on that handout I hope will be useful for the homework problem. But what I wanted to mention to you is if you actually look at problem 42 in the book, it's describing material types and pipe diameters. They're different than the handout. So actually do what the problem says in the book, but the steps, the step-by-step explanation of how to solve the problem, hopefully the handout will be useful for that. But I did just want to clarify that apparent discrepancy. All right. So today we're going to be talking about the Hardy-Cross method, which is sometimes also called the loop method. Before we get started with that, are there any questions related to what we discussed in class last time, the nodal method? All right, well, if we do have a few minutes at the end of class, I have one slide where we can talk about some of the key ideas of that problem with the constant head tanks. But it's actually nothing new that isn't already on the handout that I gave you, but we'll reserve a little bit of time at the end of class for that. So the Hardy-Cross method, let's talk about it. What's it a method for? Well, it's a method for determining what the flow rates are going to be in a pipe network that is relatively complex. And so a pipe network like this, where the water is coming in one place and it's going through several different pipes before exiting in more than one location, we can't just look at a network like this and automatically know how much of the water is going to go through each one of those pipe segments. So this method answers the question, how much goes through each pipe? And let's talk about a little bit of the background on this method. First of all, as you might have guessed, the direction that we're going in this course is that you make a guess, you do some calculations based on the guess, and then you try and improve on the guess when you find out that actually it wasn't exactly right the first time around. So here, when we apply the Hardy-Cross method, we're going to start with some initial guess flow rate, and it can't be any random guess. We're going to constrain the guesses that we put in so that it honors the continuity relationship. That is, if we have a certain flow rate coming in this first pipe, that same flow rate has to be going through the two pipes that connect it. That same flow rate combined. So it's not like you'd have 100 coming in and 100 going through each pipe. It would be 100 coming in and then maybe 50 through each pipe. So our guesses are going to be kind of using the continuity principle as a starting point. Now, we can do this by hand, and today we will. And you'll get the feeling that it's a little bit time-consuming to apply the Hardy-Cross method by hand. And so in class next time, on Tuesday, I'd like you to be sure to bring your laptop computer because we're going to use Excel to apply a spreadsheet automated method for calculating the flow rates through each pipe. And it takes a little bit of time to set up, but once you have the format all set up with the equations, then the subsequent iterations are very easy. You can just copy, paste as many times as you need for everything to converge. And it's pretty slick. Now, you can also do this by computer. And last semester in fluid mechanics, you had a very brief exposure to WaterCAD. WaterCAD is using the Hardy-Cross method. This semester, you'll have a much more lengthy and realistic chance to use WaterCAD for the design project that we're having this semester. And so you'll be glad when it comes to the design project that you're not trying to solve the Hardy-Cross method by hand. You'll be singing the praises of WaterCAD at that point. So it's Hardy-Cross that's working in the background. And you know, last time we discussed the idea of walking down a mountain. When you start at the top of a mountain, and regardless of what path you take, if you're up on a hill and you're walking to the bottom, you can take a meandering path to the bottom of the hill, or you could walk more directly But regardless of the route you take, your delta z is the same. So your change in elevation is the same. In the background, what Hardy-Cross method is going to be doing automatically, I mean, I'm just going to give you a series of really obscure, abstract calculations to do. But what those calculations are doing is it's balancing the energy to make sure that regardless of which route you take from the inlet to the outlet, whether some of the water is going this way, or some of it's going through the top, or some of it's meandering in between, regardless of whichever route it goes, we have to make sure that you have the same head loss, because it would be impossible for you to have a different amount of head loss, because then that would mean maybe you had 10 meters of head here and 8 there, but if you went through the other pipe, you had 9 meters of head there. And you have to have the same amount of total energy at a single location, regardless of what route you get there. So just keep in your mind some of the things that will it's easy to lose track of the big picture when you're doing the Hardy-Cross method because there's so much detailed, intricate application of these abstract formulas. But what's happening in the background is we're balancing continuity and trying to get energy to work out that any one of the paths has the same energy loss, regardless of which route we take. Okay, so any questions on that before we get into it? All right, well, here's the starting point. We're going to simplify the Darcy-Weisbach equation and calculate some of the terms that are constant and don't vary as a function of the flow rate Q. Remember that when we say the Darcy-Weisbach equation, usually we're writing H sub f is FLV squared divided by D to G. And we could also write that, if we didn't want to write it in terms of velocity, but if we wanted to write in terms of flow rate instead, we could write FLQ squared divided by D to GA squared. This takes that a step further. It says, for this pipe network here, where we're trying to find out how much goes through each path, there are some things that are constant. And those things that are constant that we could just group together, we're going to call it R. We could group together the F, L, D, 2G, and A squared. F's going to be changing a little. So it's not strictly speaking constant. You know, if you have a really bad guess of flow rate, then that would throw off your value of F. But for now, let's just say that if we have a reasonable estimation of F, let's say maybe we applied the fully turbulent flow assumption, then in that case, F would be constant. Because remember, the fully turbulent flow assumption just says it's only the relative roughness that dictates the F value. It's not some increase in a Reynolds number. All right. So we're just substituting R into the Darcy-Weisbach equation. And this power, this squared, we've replaced here with the n value because we could, if we wanted, use the Hazen-Williams equation in the Hardy-Cross method. Remember, Hazen-Williams is sometimes easier for us because friction factors are constant and they don't have to be iterated. And so in the handout I give you a little bit later, you'll see that it says, are you going to use Darcy-Weisbach? If so, have n equals 2. Or if you're using Hazen-Williams, you'd use n equals 1.85. But we won't ever use the Hazen-Williams equation because we're going to just go all the way. You know, we're going to use the more complicated but more accurate Darcy-Weisbach approach. So we'll just always substitute n equals 2 there. Now R can also include local losses. All we'd have to do is have some of the k values term built into when we're calculating R. But for simplicity's sake, in the example that we're working today and in the homework assignments that accompany, we'll only consider the friction losses and not the local losses because the local losses are oftentimes relatively minor in comparison. So here's what we'll do for R. We'll find the F value based on either fully turbulent, or maybe we will already know the flow conditions and we can calculate the F value directly by the Jane equation. And then all the other known parameters related to pipe geometry and length. So you've never calculated an R value before. Let's give it a shot, just to warm things up. Here we have 400 liters per second going through a large diameter concrete pipe. Concrete's relatively rough, so our epsilon value here is 1.6 millimeters, and the pipe segment's 85 meters long. So calculate R for these conditions. Oh, I don't remember that song from the 80s. Oh. I wouldn't have minded if the ringtone was something good from the 80s, you know? All right. So we got to put the flow rate into cubic meters per second, blah, 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 get the velocity, Reynolds number, F value. All right. So that's the R value. What do we do with it? Well, if you knew that R value, you could calculate head loss. So let's say, we've just been talking about this pipe. Now that you've calculated the R value, if I said how much head loss is there, well, what you could do is head loss, HL, is going to be RQ squared. And so our R value is 0.715 times Q, which was 0.4 cubic meters per second. We square that. So we'd be able to find out how much head loss there is through the pipe.
What is R?
I'm not sure why it's given the variable R, but resistance is maybe, let's call it resistance. R is the resistance. Because the longer the pipe is, will increase the resistance. A small diameter pipe would increase resistance. A big diameter pipe would decrease it. Well, the units are that way just because of what we're then going to be doing with it. We're going to be multiplying R by flow rate squared, and we want the left-hand side, we want it to equal meters when it's finished. And so we've got meters sixth second squared, and we want meters over here, so it's going to have to be second squared divided by meters to the fifth. All right. Good question. So that was just a preamble to something we have to have, we have to be able to calculate R values to do the Hardy-Cross procedure. Okay, so here's a pipe network. You're going to see a lot of diagrams like this, and it's two loops, and the fact that it's loops makes it especially hard to know how much flow is going through each pipe because it's indeterminate. We've got water coming in at one location, exiting at 3 locations, and here the R values are provided. Again, R is resistance, and so the higher the R value is, we can expect that, relatively speaking, water is going to prefer to flow through lower R value pipes. So this 100 units of water that enters the network faces a decision. It's going to go 2 directions. Some of it's going to go through this pipe, some of it's going to go through that pipe, and in this procedure we have to start with the guess value. And the guess value has to honor continuity. Whatever flow rate we determine for these 2 pipes has to add up and equal 100. And so we could just say split it 50-50, or we could try and make it so our solution converges a little faster, and we could say 60 through this pipe and 40 through the other, under the rationale that the pipe that has less resistance is going to experience more flow. There's a series of questions and steps that we're going to go through one at a time as we find out what's the flow rate through each of the pipes in this network. And I have a handout so that it can make it a little bit easier for you to follow along as we work this example. Now, this is one of those cases where I'm really sorry we don't have all the whiteboard space that was available in EL 101. That little whiteboard is going to be pretty cramped for what we need to do today. Yeah. We had a professor when I was an undergrad that we accused him of sharpening his chalk because he wrote so small, we didn't see how he managed it. He insisted that he didn't, but to this day I wonder. Okay, everybody get a copy of the worksheet? One more? Where was that? There you go. All right, so some of these questions we can answer just by looking, right? How many loops are there? 2 loops. We have to label them. Let's call this loop, loop 1, and this loop we're going to call loop 2. Yeah?
We don't count the outer circuit.
Good question. That's right, we don't. Yeah, we wouldn't then count this exterior one as a third loop. There's only 2. The end value we're going to be applying,
Can you show me those loops again?
loop 1 is here, and loop 2 is there. All right? The end value is 2 because we're going to be using the Darcy-Weisbach method of accounting for pipe friction. Now, under step 3, define direction, we have to assume some positive direction for flow, and we're going to say that clockwise is positive. So when water is going, let's see, here's our loop. If water is going this way for flow, I'm going to call that a positive flow rate. And when I put the numbers into my method, if it was 10, I would put positive 10. But if I had flow going this way, that's against my positive direction of flow. Clockwise is positive, but this is going counterclockwise in the loop because this is positive. So any flow magnitude that I have for that pipe, whether it's a guess or an updated guess, that's going to be negative because of its direction. That's what we mean by define direction. Now, label the pipes and the loops just for ease of reference, and then assign guess flow rates. R values are already calculated, and then the rest of this stuff is pretty abstract, so the best way to learn it is to do it. Now here's the formula for correcting our guess values of flow rate. So delta Q. This is the energy balance method. This is kind of the genius of the Hardy-Cross approach, is finding some way to look at, for the entire loop, how much are we off in the amount of energy that there should be, and then correcting our guess and finding out where to distribute the correction. All right, so on the second page of your handout is that same pipe network. And let's give some labels just to make things easier. Let's label this junction 1. You can write that on the handout that I've given you. Let's label this junction 2. So now we can refer to pipes. The name that we can give them will be by their starting and end junction. This is going to be junction 4, and then here will be junction 3. And then I'm going to give names to the loops as well. I'm going to call this bottom one loop 1. It doesn't matter. It could have been either way, but loop 1. And loop 2. All right. So I'm going to put on the board these columns that are shown there. I'm just going to start with iteration, loop, pipe, N, R, Q, R times Q times absolute value of Q, N times R times absolute value of Q, delta Q, and corrected Q. All right, so our first iteration 1, we're going to begin by doing some calculations on loop 1. So you can follow along. You can write, and actually I'm going to ask you to do some of these calculations, so I'm not just up here writing on the board. The pipes that I've got, I need to put in pipe 1-3. So 1-3 is one of my pipes. I'm going to have pipe 1-4 and pipe 3-4. I feel bad for the people who are watching this video right now because this isn't going to be really a lot to look at, but I will put the solution to our example on the screen when we're done with it. So, okay, the N value for each of these is just going to be 2. That's what we're using, the Darcy-Weisbach equation. So N is 2 for all 3 of those pipes. The R values are given on the screen here already. Usually you'll have to calculate the R value using the method that we've already just talked about. It would depend on what the pipe is made of, its diameter, etc. Okay? So our R values, we've got an R value of 3 for pipe 1-3, 6 for pipe 1-4, and 5 for pipe 3-4. They're just taken straight from the drawing. Okay, the flow rates. This is where the students sometimes just really struggle to know what to do, is that first, like figuring out how much flow goes where. It doesn't matter as long as at each junction the continuity relationship is valid. So this 100 that comes in, I think, is the natural place to start. 100 is coming into junction 4. We have to figure out, just assign it, how much is going in each place. And it's a guess. And so let's do this. Let's say that pipe 3-4 gets 30 of it. So 30 is going to the right. Let me just do a little sketch down here on the bottom of the board for that initial flow balance. We've got flow coming in. We've got flow going out. So it's 50 going out here, 100 coming in here, 30, and 20 coming out. Okay, so what I'm saying is let's say 30 goes this way, and that means that how much has to be going through pipe 1-4? Has to be 70, right? Okay, so we've balanced the flow there. Let's do this next junction. If we have junction 1, we've got 70 coming into junction 1 through pipe 4-1. 20 is going out. So we have to decide how much is going to go through each of these 2 pipes, through pipe 1-2 and through pipe 1-3. I'm going to say that, let's see, we've got an extra 50, right? Because 70 coming in, 20 going out. That means we've got 50 that we somehow have to assign to these 2 pipes. So I'm going to say, let's just assume that this pipe 1-3, gets 25, and that means that this also, the pipe 1-2, has to be 25 as our first guess. Yes? Good question. Yeah, that's a bad guess, isn't it? It would be better if we switched that. Maybe if we had 70 and 30 the other way. So there's no justification for our initial guess. The beauty of this method is that even when you make a stupid guess, with enough iterations, it'll still converge. It's not going to throw things off. We could have said 99 and 1, and it would still get there eventually, as long as continuity was honored. Yeah, thanks for asking that question because that is a poor guess. Was there another question over here? Yes. It's been a long time since I took the FE. Of course, I work on it, but I don't know that I can answer that. How often? The questions are supposed to last 2.9 minutes. That's the most meaningful response I can give you. Yeah. Well, the answer's there, right? 2.9 minutes. We couldn't do this in 2.9 minutes. Yeah. All right. I couldn't. Not in 2.9 minutes, no. Nope. All right. So we did flow balance at junction 4 and junction 1. What's up at junction 2? We've got 25 coming out and 50 going out. We've got 25 coming in, 50 going out. So that means we have to have 25 coming in, and fingers crossed that that ends up working out. So let's look at junction 3. Does everything balance at junction 3? Does the in equal the out? We've got coming in 55, going out 55. So continuity works, all right? And it's not coincidence. I mean, as long as you make a correct split at each step, then that last one will just miraculously end up where it needs to be. But just to emphasize again, this isn't the only correct flow balance that you could use in your first iteration. It could literally be anything. But let's look at our directionality. Remember, clockwise is positive. So when I start writing in my flow rates here, for pipe 1, 3, for example, pipe 1, I better just write the junctions on here. 1, 4, 2, and 3. Okay. Okay, so pipe 1, 3, the flow rate needs to be positive. Because here it is, 25, and it's in the same direction as that clockwise. So the flow from 1 towards 3 is going in the clockwise direction. So that's a positive 25 for Q. Pipe 1, 4, positive or negative 70? Because here we're looking from the perspective of loop 1. We're in loop 1 right now. If we were looking in terms of loop 2, it would be negative, right? So that one in the middle, pipe 1, 3, is a little tricky because its direction changes depending on which loop you're in. Right now, our mindset is the loop 1 mindset. Thanks for asking that. Okay? Pipe 1, 4, positive or negative 70? Positive, yep. And then this flow through pipe 3, 4 is negative 30 because it's going against the arrow. All right. So this is where you whip out your calculators and calculate for each row the R times Q times absolute value of Q, the N times R times absolute value of Q, and then we'll talk about, once you do that for each row, we'll talk about how you calculate the delta Q. You can attempt it, but sometimes it's a little tricky, so we'll go over it together. All right, so you've calculated the R times Q times absolute value of Q for pipes 1, 3, 1, 4, and 3, 4. If you add all of those three numbers together, you should get 26,775. And then if you do the N times R times absolute value of Q for those three pipes, the sum is 1,290. What we're going to do now for the delta Q, this formula that's on the screen there, we want to have our delta Q is equal to the negative of the sum of R times Q times absolute value of Q, so negative 26,775 divided by 1290. And so the delta Q that you should get is negative 20.756. That's what we're going to use for each one of the pipes, actually. So now that I've done these calculations on the board just to show you where this came from, I'm going to erase it and I'm going to write it on there 3 times. So it is negative 20.756, negative 20.756, negative 20.756. Now, that is how much we need to correct in our next step. So the flow rate, the corrected Q, is 25 minus 20.576. And so my corrected flow rate is 4.24 for pipe 1-3. My corrected flow rate for pipe 1-4 is 70 minus 20.756. So that gives me 49.24. And then for the final pipe was negative 30, so you combine that with the negative 20, and we're getting negative 50.76. So we've now completed the iteration 1 for loop 1. Now we're going to look at things like what's going on in loop 2. We're still in iteration 1, but now we're going to be looking from the perspective of loop 2. So the pipes in loop 2 are pipe 1-2, pipe 2-3, and pipe 1-3. Remember, pipe 1-3 is also in the first loop, but we have to look at it in both loops. So our N value is 2 for all of those. Our R values we can get off of the drawing. So it's 1 for pipe 1-2, 2 for pipe 2-3, and 3 for pipe 1-3. Okay? And the flow rates. We're going to do a similar thing as we did, just looking at our flow balance sketch. We've already defined our first flow balance. I see the beginnings of a question in the back. Ah, brilliant. Yes, you do. Yeah, so he's asking for pipe 1-3. Do we use our original guess value of the flow rate, or do we use the new and improved version of the corrected Q? And that's what we use. We use our corrected Q. But not only do we have to remember to use the corrected Q, but we have to be careful because the sign is going to change. Because before, that flow rate was positive when we were in the perspective of loop 1, but now when we're in loop 2, it's negative because it's against the arrow. So here in 1-3, I'm going to say it's negative 4.24. It will later, but pipe 1-2 and pipe 2-3, we just take straight off the drawing. So the only one we have to remember that, well, we don't have any better information at this point. The general principle is always use your latest guess or calculation of flow rate. And our latest guess for pipe 1-2 was 25. And our most updated guess for 2-3 is negative 25. Does everybody see that? Negative because it's going up from 3 towards 2, so it's against the clockwise direction. But then the tricky one is the common pipe, pipe 1-3. Okay, so now that you've got those, calculate both the R, Q, absolute value of Q, and the N, R, absolute value of Q. Yes?
Why would we not go ahead and update our guesses for 1, 2, and 3 to violate the options?
Good question. We don't have updated guesses, and this will self-correct. The Hardy-Cross method is when it balances the energy, it's going to self-correct that. And at the end, let's revisit that. Let's double check that our solution, when we're done, not only does it have the right head losses, but also we want to make sure that it still is honoring continuity. Because any solution that isn't honoring continuity, we can throw that out, and we know that it's ridiculous. But I see your point, but there's just nothing else we can do it quite yet. Okay, so do those calculations. In this case, find the delta Q. You know how to do delta Q now. So find the sum of each column and then calculate the correction factor that we need to apply. That minus sign is sometimes easy to overlook. Don't overlook that minus sign. I'm going to have to erase our diagram of flow balance, but we are going to revisit continuity when our solution is converged, just to make sure that everything is the way that it needs to be. Okay, so we calculated the R, absolute value of Q. Why is it we don't just have RQ squared? Wouldn't that be, you know? Exactly. We need that negative sign. We need to know if it's too high or too low. So it's to keep the directionality of it. And the same thing is not true, though, in the case of n times r times absolute value of q. We want those negative signs to go away when we're calculating that column. So when you calculate the delta q for this loop, for loop 2, iteration 1, now we're correcting by 3.87. Now here's something you should look for. You should always be seeing your delta q's be getting smaller from iteration to iteration. Question? Well, you know, we're going to be getting into Excel, and Excel will keep all of the precision in the back of its mind and just only display as many digits as we want to see. And spreadsheets can get so overcrowded with excess numbers if you let them that I'll usually turn it down so I'm only seeing 1 or 2 digits, but then I feel comfortable because I know that I'm not actually losing any precision. In your case, I think 4 digits of precision is good to have on the paper just so that you've got them for the next round. So it could, like if we rounded this to 4, things would get pretty sloppy. But 3.870 will be all right. Are there other questions too? All right, so let's just set up the next iteration, but not actually crunch the numbers with it, because I don't want to wear out your antique calculators, all right? So, actually, I've been teaching Engineering 111 this semester, and it's the first time I've been in a position where I had to learn the Casio, and it's all right, I guess. But what would I suggest? Oh, well, don't even get me started. Oh, I know. Somewhere, Bill Pearson is like ears are burning, and he feels like a stabbing pain in his back. Yeah, Hewlett-Packard, HP 50 is the calculator to use. Like $100. If you buy it on eBay, you could get a used one. But I still have my calculator that I bought in '93, and I still use it. So it's the calculator that lasts a lifetime, right? So. You can use reverse Polish notation, which is awesome, but you don't have to. Fewer keystrokes when you're solving equations. We'll have an we'll have an HP lecture one of these days. I'll take you all over to the dark side. But for now, you can keep using the Casios. All right. Did I say that with enough dismissiveness? Was that subtle enough? All right. So iteration 2, loop 1. All right, so I hope it's obvious that this is, if there was ever a case for copy and paste automation, this is it. We're going to write it again, but if we were using Excel, we just copy, Control-C, and then put it in the next row down, Control-V, paste. And we'd have to make a few adjustments, but the structure would be there. So we're going to have pipe 1, 3, 1, 4, and 3, 4. Okay, the N values haven't changed. The R values haven't changed. Not in this problem, but now I need to make you aware of something. When we are working together on Tuesday, we're not going to actually calculate R values. We'll calculate the F values. And the F values will be changing. Because remember, F values are a function of flow rate. And so if you have a different flow rate, our initial guess was 25. We could calculate some F value based on that. But now, if it turns out that 4 is closer to the truth, we're going to have a much different F value. So here, I'm writing the same R value, but that's just because I'm trying to teach you about the method today, like the structure of the method. And we'll get into more of the fine details on Tuesday. So here, R is the same. Tuesday, it's not going to be the same because we're actually going to be accounting for the fact that a changed flow rate means a changed F value. What Q should I use for pipe 1, 3? Positive 0.37. Very good. Because I want to use my latest and greatest flow value. If I had just done copy paste, like with Excel, then it would have said 25. That's one of the things that I would go and I'd change is I'd say, I need to do equals negative of whatever value is in that cell. Because then it would change the sign, and having it as a reference instead of just typing in 0.37, having a cell reference allows me to then copy and paste for a subsequent iteration, and everything's going to be relative. All right, what about pipe 1, 4? What flow rate do I have there? Yeah, I don't have anything better from loop 2 than 49.24, and the same thing is true of pipe 3, 4. I need to have negative 50.76. Okay. Mm-hmm.
What are we trying to convert? What are we doing?
We're looking for these delta Q's to be so small that there's no reason to apply them anymore. Meaning that the flow rates aren't changing from iteration to iteration. And when that happens, we're going to double check that the ins and the outs are equal at each junction. Great question. I'm glad you were asking. You're thinking in terms of when do we get to quit? Like what's the conversion criteria? Do we do this forever? No. We do it until the delta Q's are small enough that like 1% change is a good enough convergence. Are there other questions? Okay. So rather than doing RQ, rather than actually doing everything, I just want to show you what the solution to this is. So let me bring up the Excel version of this. Okay, so here's what we already knew. Here's the flow rates we already knew. Here's the loop 2. All right. So here we've got the reverse of the flow rate from the opposite pipe. Here's the RQ, absolute value of Q's. Here's the sum. Here's where my delta Q and the corrected Q. So the question is, are things on the right track? What are some preliminary indicators that things are headed in the right direction? Well, number one, our delta Q is getting smaller. That's a good sign. We had to correct by 20 in the first stage, and now we're only correcting by 1.5. So even though I had kind of a sloppy guess for that first flow balance, the 70-30 split that kind of seemed a little unjustified, still, it's converging pretty quick. That delta Q got a lot smaller. And the same thing is true for loop 2. We had 3.87, and now it's down to 0.373. So when we use Excel on Tuesday, we're just going to then take iteration 2, copy, Control-C, and then we're going to paste iteration 3. And the hardest thing we'll have to do is we'll have to change this number 2 to 3. And that'll be like the grand total of our efforts for the third iteration. Because it'll remember all of the relative references from before, We're going to have these nice small delta Q values, and now the flow rate is it's converged. You know, here's the beginning guess, here's the end guess. It's not really changing. And another way to know that everything looks good is look at pipe 1-3, that common pipe. It's the same flow rate here, 1.51, as it is in the perspective of the other loop. So it's 1.51 in both loops. So that's another good sign. But let's do the last step here is to draw our diagram and make sure that continuity is honored at each one of those junctions. Okay, so we had, here's our network, 20 coming out at junction 1. We have 50 coming out at junction 2. Junction 3, there's 30. And 100 is coming in at 4. Like, why is that much going in? And why is that much going out? Well, maybe it's because connected to junction 1 is a golf course. And they've got the sprinklers on and they need 20 right now. And maybe at 50 is a fire. And they're putting out a building fire. You know, there's just some demands. And the network has inflows to satisfy those demands. And so it's not that we're forcing in 100. It's that there's some positive pressure in the network at junction 4. And there's enough pressure there and enough available water to satisfy these demands. So if you're just sort of wondering about, like, what's the actual engineering design application of this, you have to know what the system demands are and then assign those demands to the system. And then we're kind of interested in, well, all right, in that case, how much flow is going through each pipe? Because once we know how much flow is going through each pipe, then we can calculate the pressure at each junction and know whether there's enough pressure. As people get very irritated when they turn on the shower and it's just a trickle. They like a blast when they're taking a shower. And so if they're not getting a good enough blast, that means we have to move the reservoir higher on the hill or increase the size of our pumps. That's what you're going to be doing, or change the pipe sizes. But let's check continuity here. Okay, so in our final solution, we said that pipe 1-4 has a flow rate of 47.73. And that's a positive, which means it's going this way. Okay, so 47.73. Pipe 1-2 had 29.24. And from the perspective of loop 2, that was positive, which is why I'm drawing it from 1 towards 2. That was 29.24. Pipe 2-3 is negative 20.76, and so that means it's up from 3 towards 2. Okay, negative 20.76. I don't actually write the negative value on the drawing because it's the arrow direction that takes care of the sign of that. Pipe 3-4, 52.27. From the perspective of pipe 1, that's negative, which means it's that direction, 52.27. And so then our final one, pipe 1-3, okay, I'm looking at it now in terms of loop 2. It was positive in loop 2, which means the flow is going that way. All right? So 1.51. Okay, well, let's check at junction 4. In has to equal out. So what is 47.73 plus 52.27? I really hope it's close to 100. Is it? We'll double check. All right. Even the Cassius could get that one, right? All right. Okay, so we're good at junction 4. Junction 1. Okay, we've got coming in 47.73 plus 1.51. What is that? In 49.24, and our out, I can do this math, 49.24. See how I did that? All right, junction 2. We've got 50 coming out and coming in, so 20.76 plus 29.24, that's 50, right? I can do that math too. So it's looking good so far. Our last one, we're in the home stretch. Coming into that junction is just this one, just 52.27. So here is 50.76. I think that's 52.27. Yeah. Yeah, all right. So continuity is honored. So we have a valid solution. The solution is converged. That's the method. So now I think that you've seen that in action, this list would probably make more sense. The step-by-step process of what you're supposed to do. Any lingering questions about all that? Yes?
So if one of those areas, say up here, figure that experiences 70, wouldn't that cause a pressure drop in the other areas?
Can you?
Outflow is greater than the inflow. Would that cause a rise in pressure?
There can't be more out than coming in. Yeah. What causes a massive pressure drop is when you have a big flow rate through a small diameter pipe. You know, head losses are proportional to flow rate. And so this same network, if instead of 20, 50, and 30, you know, like we could calculate the pressures at each of these junctions right now. If we knew a little bit more information, if we knew the elevation and we knew the pressure at a control point, if we knew the pressure at one junction, we could calculate the pressures at the rest. But if you increased the flow rate and kept the pipe diameters the same, then the pressures would go down. But you can't have more flow coming out of a network than is going in, unless there's a reservoir somewhere, you know, like a tank up on a hill that's allowing the flow to equalize. Any other questions? All right, this one. Now that you've done the Hardy-Cross method, you may look at this and say, hey, there's a loop. I want to apply the loop method here. But it's not. You need to solve this one by the nodal method, which is what we talked about last time. So you have to assume a flow direction to solve this problem, and continuity has to be satisfied when you do that. And we know the head at A and B because it's immediately connected to these reservoirs. So we know that head decreases in the direction of flow. That is, there's energy loss in the direction of flow. Let's just go back to this first step, though. You've seen how we can draw a little network on the board and then like sort of do a breakdown of the flow directions. What if we have this one? Okay, we know that flow is coming in at C, 0.2. Flow is going out at D, 0.2. That was C. Here's A. Here's B, I guess. And what it doesn't show is that it's constant head at the tanks. So the head is always going to be 25 at A, but flow could be coming out of tank A and going into tank B. That's possible that there is water going from A to B. And so let's assume that, just for sake of calculations, the flow is going this way. It's going from C towards A and going from C towards B. So now if I'm going to write the energy relationship, I would say that the head at C is the head at A. And if the water is going from C towards A, then that means that the head at C has to be bigger than the head at A. So plus, and then R times Q squared. Does everybody see that when you assume a flow direction, you also are assuming that head at one location is bigger or less than at the other? You know, like water flows from high energy towards low energy. So if I assume this flow direction from C towards A, I'm also assuming that the head at C is more than 25. And so then I would also say the head at C is the head at B, and now it's going to be plus, because I'm going opposite to flow, plus RQ squared. And the Q that I was talking about in this first equation was QAC, and the head I was talking about, the flow rate I was talking about in the second equation is QBC. And then the other thing I know is that QAC plus QBC is equal to 0.2. So now I've got these equations, and I could do the same thing for D. I could say how much head is there at D in terms of some assumed flow direction. If you assume a flow direction, then what we're saying here is that the head at D is less than the head at B, and that the head at D is less than the head at A. Otherwise, why would water be flowing from A towards D, and vice versa? So continuity must be satisfied. We know the head at two locations. We have to calculate the head at two others in terms of the flow direction. Now, you can make a bad guess. Maybe the flow actually is going like this. Yeah, it's possible that it could be like that. Now, if you set up your system of equations and you're solving for the Q's, you know, you've got two equations, two unknowns, you're solving for your Q's, and if you end up with a solution that has like imaginary numbers in it, then that tells you your initial guess of flow direction was wrong, and change one of the pipe flow directions and start it over again. You can use the fully turbulent flow assumption to begin because you don't know what the flow rates are, but then you should check that assumption to see if it's valid and make adjustments as necessary. So take a crack at it. There's detailed explanation on the handout, and I'll take the solution to this one home with me over the weekend so that if you want to send me an email, I'll try and be prepared to answer your questions. I also have office hours, so feel free to stop by. Have a good day, guys. I'll see you on Tuesday. Bring your computers on Tuesday.